Hello students, we today discuss type of vibrating rotor, that is vibrating molecule or any vibrating body. Depending on vibration motion, that vibrating bodies are classified into two types, that is harmonic oscillator and unharmonic oscillator. Consider first harmonic oscillator. That if we consider that molecule or any that vibrating body, so as to explain that vibrating motion, if we consider molecule as a ball and spring model, then in ball and spring, which are not exactly same as that actual molecule, here we consider that is a model, and therefore when that balls during stretching go away from each other, that stretching of spring takes place, and when in compression that balls come very close to each other, during stretching and compression in the ball and spring model, there is no any forces, that is during stretching, long stretching, there is no fear of breaking of that spring because spring is stronger than actual bond. And during compression, that when that balls comes closer, then that balls in the model, there are no any electrons and nuclei present in that model balls, therefore no any force development of no any force during compression when that balls come closer. Therefore such vibrating motion of model is considered as a harmonic oscillator. There is no any difficulties for vibrations in this molecule. And for harmonic oscillator, the vibrational energy is given by equation similar to molecule, that is U vibrational is equal to phi plus half into H phi 0. And because of motion, vibrational motion, potential energy developed in such a molecule is in molecule also, potential energy is equal to half k into x square. That k is here force constant. K is force constant, which depends on that value of k depends on that strength of that bond in model, strength of that spring, and x is displacement from mean position, that is displacement from mean position, that is during stretching there are considered three positions. First is mean position, second one consider stretching, that balls or that atoms go away from each other, and third one is next step what happen, again mean position, and next one is compression, that atoms or molecules atoms or that balls, atoms in the balls, atoms in the molecule, or that balls in the molecule come closer, that is compression. In compression value of x is decreases, and in stretching value of x increases. If we consider graph showing potential energy against value of x, this one is shown in diagram. That is, as displacement from mean position, value of x increases, potential energy also increases. When vibrational motion is small vibrations, vibrational speed of vibration is low, at that time displacement from mean position is also less, small displacement. At that time potential energy is also less. But as the speed of vibration increases, that atoms stretching, maximum stretching takes place. That atoms goes away from mean position, and therefore with increase in vibrational motion, increase in value of x, and therefore increase in potential energy takes place. This is a graph showing change in P against X for model, not for actual molecule. This is for model, that is spring and ball model, where no any difficulty exists during vibration. For vibration in model, no any difficulty. Therefore, that diagram shows, that graph shows parabolic nature, and above equation of PE of that model is also equation for parabola. Then consider unharmonic oscillator. Unharmonic oscillator. If we consider actual molecule, if we consider vibrational motion in actual molecule, then there are two difficulties exist during vibration. The first difficulty is that during compression, atoms come very close to each other, and atom consists electrons and nucleus. Therefore, because of that very close distance, that there is development of repulsive force of repulsion between that electron of that two atoms and nucleus of that two atoms. Such type of repulsive force is not exist in model, but that exists in actual molecules because of that electrons and nucleus exist in atoms in molecules. And second difficulty for vibrational motion of actual molecule is that bond is in model, bond is considered as a spring, but in actual molecule, how that chemical bond is developed? By overlapping of atomic orbitals, and when extra stretching, maximum stretching takes place during vibrational motion, then what happen? There is possibility of breaking of that bond. That is when when atoms goes away from each other during stretching, orbitals also goes away from each other. Then no any overlapping. That overlapping breaks. Overlapping may become zero. That is nothing but bond breaking maybe takes place. These are two problems, and therefore vibrational motion in actual molecule not as ideal as a model. There is because of these two changes, there is change in that graph for x versus potential energy. That graph for actual molecule in this diagram, that dotted line indicates that graph for P against X graph for model, which is parabolic, while that red line graph indicate that P against X for unharmonic oscillator, that is actual molecule. That graph shows that when value of x is small, then that two graphs overlap with each other. That means molecule also behaves as a model, ideal. Vibrational motion is ideal. Because for small vibration, small magnitude of vibrational motion, the two problems are not there. No maximum compression, therefore no development of the triple force of repulsion, and no maximum stretching, therefore no possibility of overlapping, zero overlapping. These two possibilities are not there for minimum vibrations, and therefore when vibrations are minimum, when vibrations are slow, at that time value of x is small, and therefore molecule behaves as a model. But as vibrational motion increases, x increases, and then because of the two problems, molecule behaves not as a model, and that graph not overlap afterward with maximum x, and that is unharmonic nature of that vibrational motion in molecule, that is known as unharmonic oscillator. Therefore actual molecule is considered as a actual vibrating molecule is considered as a unharmonic oscillator, and model considered the ball and spring model is considered as a harmonic oscillator. Then for such vibrating unharmonic oscillator, that vibrational energy is given by E. This one is directly given equation on the basis from quantum mechanics, that is E vibrational is equal to phi plus half hv0 minus phi plus half square, phi plus half bracket square into h phi0 into xe. What is xe? Xe is displacement during vibrations in molecule. Then based on this, by considering molecule as a unharmonic oscillator, we discuss here that expression for change in vibrational energy of an unharmonic oscillator, change in vibrational energy for unharmonic oscillator. This is very important point as per exam view. Expression for change in vibrational energy. Remember, change in vibration energy of unharmonic oscillator. The potential energy of an unharmonic oscillator is given by that previous equation we discussed already, that is E is equal to in bracket phi plus half hv0 minus phi plus half bracket square hv0 xe. Then so as to calculate change in vibrational energy, that is delta E, consider two vibrational energy levels, E1 and E2. And delta E, that is change in vibrational energy, is equal to energy in final state minus energy in a initial state, that is E2 minus E1. Then above equation we write for E2 and E1, and substitute in this equation, delta E become equal to, then by solving, rearranging, we got phi2 plus half hv0 minus phi1 plus half hv0, that hv0 terms we collect together, minus phi2 plus half bracket square hv0 into xe minus phi1 plus half bracket square hv0, that is both are bracket square terms. Therefore by solving first term, phi2 minus phi1 into hv0 minus in brackets terms that HV0 Xe become common. Therefore, that V2 minus V1 into HV0 minus, by solving that brackets, V2 plus half plus V1 plus half. V2 plus half plus V1 plus half, that is first bracket by solving. Then my into V2 plus half minus V1 minus half into common is there HV0 Xe. Then by solving that, V2 minus V1 HV0 minus V2 plus V1, rearrangement is there, V2 plus V1, and that half that become 1 plus 1, and in another bucket V2 minus V1, because plus half and minus half cancel to each other, therefore V2 minus V1, and common is HV0 Xe. Then if we consider first term, that is V2 minus V1 into HV0, and another minus another term, then in these two terms, what is common? That V2 minus V1 into HV0 is common. Therefore, consider that common term. Then in bracket, what is there? 1 minus V2 plus half, V2 plus V1 plus 1 into Xe. Xe is not common, therefore that remain inside. And we know that delta E is equal to H into mu. H into mu. Therefore, substitute that value. H will goes at this side and cancel. Therefore, frequency mu is equal to V2 minus V1 into V0. Here H cancel. In bracket 1 minus V2 plus V1 plus 1 into Xe. Then mu is equal to, we know that mu bar, consider mu bar. Therefore, that mu bar, that is wave number, frequency in a wave number form, V2 minus V1 into mu 0 bar in bracket 1 minus V2 plus V1 plus 1 into Xe. This one is a equation for that change in vibrational energy for that molecule. By using this equation, we calculate that change in vibrational energy during different vibrational transitions, that is vibrational excitations of that molecule. What is selection rule for this vibrational excitations? Here for unharmonic oscillator, selection rule is delta V, that is change in vibrational energy level during transition. Vibrational transition is equal to plus minus 1 plus minus 2 plus minus 3. All these vibrational transitions are allowed. Then consider first transition, which is nothing but known as, that is delta V is plus minus 1. Delta V is when plus minus 1. This is known as fundamental transition, fundamental mode. Then for this vibration, V1 is 0. First line in this, for this selection rule, V1 is 0 and V2 is 1. Then only that V2 minus V1, that is delta V, that is 1 minus 0 plus 1. Delta V plus 1, therefore V2 minus V1 is plus 1, therefore V2 is equal to 1 plus V1. V2 is equal to 1 plus V1. Substitute these both values, values of V2 minus V1 is 1 and V2 is equal to 1 plus V1. V2 is equal to 1 plus V1. In above equation, that is that frequency wave number is equal to in a main equation. Then if we substitute, we got that V1 bar is equal to that or mu1 bar is equal to mu0 bar in bracket 1 minus twice xc. 1 minus twice xc. By solving above and that V1 consider as a 1, then this become V1 bar. This is wave number of first line. Wave number of first line. That is known as fundamental line. Then consider case 2. That is delta phi is plus 2. Delta phi is plus 2. Change in vibrational quantum number plus 2 transition. That is 0 to 2 direct. 0 to 2. That is V1 0, V2 2. Then that V2 minus V1 become plus 2. V2 minus V1. That is 2 minus 0. That is 2. Therefore, what is V2? V2 is equal to V1 plus 2. Substitute these two values, that is V2 minus V1 2. V2 minus V1 is equal to 2 and V2 is equal to V1 plus 2. Substitute these two values in above equation. Then V2 bar is equal to 2V0 in bracket 1 minus 2V1 plus 3 into XE, but that V1 is 0. V1 is 0. Therefore, this equation become V2 bar is equal to 2V0 bar in bracket 1 minus 3XE. 1 minus 3XE. In above equation, 1 minus 2XE. Here, 1 minus 3XE. Then consider case 3. Then V1 0 and V2 3. That is delta V then become plus 3. That is V2 minus V1 is 3. V2 minus V1 is 3. That is 3 minus 0 is 3. Therefore, value of V2 is V1 plus 3. V1 plus 3. Substitute these two values in above equation. Therefore, we got final expression as a V3 bar is equal to 3V0 bar in bracket 1 minus 4XE. By considering these three equations, that is fundamental mode, then first and then second, that is equation 1, equation 2 and equation 3, that indicate that the fundamental frequency, that is delta phi is plus 1. First frequency of vibration, that is fundamental, then first and then second. For fundamental equation 1, for first equation 2 and for second equation 3. Remember that. Which one is fundamental? 0 to 1 is fundamental. 0 to 1 transition is fundamental. That is delta V is plus 1. That one is fundamental. Then what is first? 0 to 2 is first. 0 to 2 is a first. That is delta V is plus 2. And which one is second? 0 to 3. 0 to 3 is the second. That is delta V is 3 plus 3. Then that indicate that fundamental frequency V2 bar is in a ratio in order of 10 raised to 5 meter inverse, and unharmonicity constant is small, and that equation 1, 2, 3 indicates there is a ratio between that frequency of fundamental first and second overtone. Fundamental first and second overtone bands are roughly as in a proportion of 1:2:3. This one we can write from equation 1, equation 2 and equation 3 from that previous page. Thank you. This one is very important point. On this article there is question on many question papers, that is show that wave number of lines, wave number of fundamental first and second overtone bands are in a ratio of 1:2:3. For 5 marks, many times this question was asked. Thank you very much.